Welcome to The Explainer. Today, we're diving into a completely mind-bending reality about the software running on literally every device you own. We're so used to thinking of code as just text, right? A sequence of logical instructions sitting on a screen. But what if all that source code, all that complex syntax, is really just a costume? What if, underneath all that surface text, an algorithm is actually a rigid physical geometry?
To wrap our heads around this, let's look at a fundamental paradox. It's an almost unsolvable mystery that's triggered a literal epistemological crisis in computer science for decades. Think about it. How do you definitively prove that two entirely different sequences of code compute the exact same mathematical outcome? Traditionally, we've relied on exhaustive input-output testing, or really complex graph isomorphism checks. But as we're going to see, these methods are incredibly fragile. They are so easily fooled by the sheer chaos of modern software compilation.
So here's our roadmap for the investigation. We'll start with the code carrier problem, then move into extracting the dependency cone, look at the geometry of SHA-256, define the computational instrument, and finally, look at what this means for a new era of verification. Let's get into it. Part 1. The code carrier problem. The absolute core of the issue here is the massive distinction between the carrier dialect and the instrument identity. Think of the source code, the target assembly language, and the execution order as just a fluid performance. It's like a musical score being played at totally different tempos by completely different orchestras with varying stylistic embellishments. That surface performance, that's the carrier ceremony. It's literally just the costume. The instrument identity, on the other hand, is the underlying force dependency aperture. It's the invariant, rigid computational skeleton that absolutely cannot change without totally breaking the function itself. The distinction between the noisy, arbitrary instructions and the unbreakable mathematical outcome is night and day. Now, the reason this costume changes so drastically comes down to something called the phase ordering problem. Just think about how complex modern compilers like GCC and Clang actually are. They're juggling massive data dependencies and strict hardware limits all at once, and they prioritize those tasks completely differently. GCC, for instance, might aggressively prioritize register allocation, which in turn severely restricts the instruction scheduler. Clang, though, it might prioritize the instruction scheduling, generating vast arrays of independent pathways that need totally different memory management. The end result is that the underlying algorithm gets aggressively scrambled and mutated right on the surface. And the data completely backs this up. When researchers took the exact same SHA-256 compression function source code and compiled it using both GCC and Clang, the surface-level instructions showed massive variance. We're looking at a stream edge distance, or L1, of 0.2267. So to a standard static analyzer just trying to read the text, these highly divergent execution rhythms look like completely different programs. The noise is basically overwhelming the signal.
Section 2. Extracting the dependency cone.
So how do we get past the noise? Researchers developed a methodical, multi-layered analytical extraction ladder to systematically discard this carrier dialect and essentially X-ray the algorithm. It works in 3 main steps. First, it parses the disassembled code specifically for constructing data flow dependency graphs. Second, it rigorously filters out all the costume elements, stripping away the stack management, the memory movement, and the control flow branching. And finally, it isolates the pure core mathematical subset. This is where we succeed in identifying the load-bearing topological signatures of computational instruments. And this leads us to the real aha moment of the entire investigation. Once that arbitrary carrier ceremony of register spilling and instruction scheduling is systematically stripped away, that massive surface divergence we just talked about, it practically vanishes. The Jensen-Shannon divergence between the GCC and Clang outputs collapses down to an astonishingly near zero 0.0071 bits. It's almost perfectly identical. When we examine the semantic transition edges, the alignment is completely flawless. Looking at the vital, load-bearing connections, like the rotate to logic edges, they are entirely identical between the two compilers. They match perfectly in count and in weight. This absolute collapse is the definitive proof that the true cryptographic instrument isn't the noisy sequence of text instructions. It's this immutable dependency cone. It's a real, physical, measurable object. Section 3. The geometry of SHA-256. The standard model usually treats hash functions like SHA-256 as an irreversible, unstructured diffusion field, basically just a giant random blender of data. But the reality? It's a continuous dynamic system. If we look closely at how the 16-word seed window feeds directly into the 48-word expansion zone, it becomes super clear. It's not a random blender at all. It's a highly structured operational trace moving deliberately through a mathematical lattice.
And the engine driving that movement is a specific mathematical recurrence equation. The schedule isn't just mixing data, it's constructing an intricate parity dual stream architecture. It creates what researchers actually call a hardness wall at round 7. This is a truly impenetrable topological vortex of chaotic structural collapse. And it's exactly this vortex that completely prevents hackers from reverse engineering the macroscopic impedance of the data.
Now, why the specific numbers 2, 7, 15, and 16? Well, they definitely aren't random. They establish a rigid geometric scaffolding. Because the leg arm spreads contamination exclusively in uniform steps of 2, it perfectly preserves a state of parity duality along isolated spines throughout the whole algorithm. It essentially forces an even and an odd processing rail that only ever merge at highly specific load-bearing cross-parity conduits. It essentially forces an even and an odd processing rail that only ever merge at highly specific load-bearing cross-parity conduits. All of this brings us to an absolutely unbreakable mathematical law governing all computational shapes, the triadic rule of algorithmic closure. Combinatorial perturbation testing repeatedly proves that true aperture closure requires a strict minimum of 3 active binding roles. If you have fewer than 3, the topology just remains an open line or a solitary point. But hit exactly 3 nodes, it resolves into a rigid topological cycle. This is the securely enclosed region of closure. It's literally the unbreakable geometric floor of computation itself.
Part 4. The computational instrument defined.
So, if algorithms actually have a physical, unbreakable geometry, how do we define the software itself? Well, we define it by its forced dependency aperture. This is the exact, immutable signature representing the load-bearing topology of an algorithm. It's completely stripped of the dialect noise, the compiler's register allocations, and the chronological execution sequence. Think of this aperture as the true, invariant identity of the software. It's the part of the machine that simply cannot be altered without totally destroying the machine itself. To map out this geometry computationally, the instrument is translated into a highly specific tuple framework. It's made up of 4 things. First, the force dependency nodes, that's the inescapable math. Then, the execution limits, which are the boundaries of transition. Next is the address carrier geometry, the strict spatial layout where the data has to reside, like the specific physical slots of an 8-word shift register. And finally, the required closure condition, which is the definitive output proof. By organizing the computation this way, the framework completely and cleanly quarantines the compiler noise. And guys, this isn't just theoretical. The Engine 25 perturbation matrix empirically validated this boundary with an absolutely perfect 18 out of 18 execution score. When researchers systematically dismantled the load-bearing nodes or edges, the cryptographic closure instantly broke. The program literally died. But when they intentionally reroute the addressed carrier geometry, swapping physical coordinate positions while preserving the mathematical sequence, the instrument maintained absolute closure. The costume changed, but the skeleton survived perfectly. Section 5. A new era of verification. Identifying algorithms by their structural geometry has massive real-world implications. Just imagine compiling software not into machine code, but into an aperture hash. This would be an automated artifact containing absolutely 0 traces of the original author's source code or the compiler's scheduling heuristics. It's purely a signature of the underlying structural intent. Because graph isomorphism is an NP intermediate problem, basically an incredibly complex matching puzzle that totally bogs down traditional computers, attackers routinely hide malware by injecting obfuscation noise. But the aperture hash? It completely bypasses that camouflage. It collapses complex, easily fooled matching into a definitive, linear cryptographic signature comparison. There's a quote from the investigation that perfectly solidifies everything we've been uncovering today. Changing carrier ceremony must preserve closure, while mutating a force dependency must inherently break closure. That right there is the rigorous standard that isolates the true formal mathematical object from the overwhelming chaos of modern compilers. So I'm going to leave you with this final thought to ponder. We've seen that the raw assembly language, the C code, the hex strings, they're really all just highly variable ways of holding the exact same executable shape. If code is just a costume, and the invariant geometric dependency cone is the true identity, How does this completely change the future of hacking, artificial intelligence, and how we actually trust the software running our entire world? Think about it. Thanks for joining me on this explainer.